Hello everyone and welcome back to Teach Astronomy. My name's Victoria, but you can call me Vicky. And today is Monday, which means we are reading another chapter in our book, Dreams of Other Worlds. So if you are new here, Dreams of Other Worlds is a book by Professor Chris Impey and Holly Henry, a professor of English at California State University, San Bernardino. And it is all about unmanned space exploration. So some of the older chapters that we read, which are all available either in our archive here on Twitch or on our archive on YouTube at Teach Astronomy. We read about Cassini, we read about Voyager, we read about the Mir rover, Spirit and Opportunity. We read about Viking, all that good stuff. And this week we are actually... I was going to say we're leaving the planets, but like Voyager focused on the planets, but also just kind of left the solar system. But today we're focusing less on the big bodies in space, and instead learning about stardust, which tried to research a comet. Hello, CJ SideQuest. Welcome. Hope you're doing well. I hope everyone's doing good this morning. But yeah, I guess we will just jump right into it because I'm excited to learn about this comet mission. I honestly did not even know that stardust was a thing. Like, I knew that we had researched comets and stuff and probably sent a probe up there, but I have no background on what stardust is. So I'm excited to learn along with y'all. And I'm just going to move my keyboard so I don't accidentally press a button with my elbow and stop the stream. All right. So let's start. Stardust, catching a comet by the tail. The story of life in the universe is a story of stars. As the first clouds of gas formed stars in the infant universe, more than 13 billion years ago, the universe contained only hydrogen, helium, and a few other trace light elements. The nuclei of these light elements were forged in the intense heat a few minutes after the Big Bang, when the entire universe was as hot as the core of the sun is now. As the universe rapidly expanded, radiation eased its grip, and a scant 500,000 years after the Big Bang, it had cooled enough for electrons to mate with nuclei, and for hydrogen and helium atoms to form. Chemistry was now possible, but a universe made of the two simplest elements is singularly dull. Hydrogen atoms can only join to form a hydrogen molecule, while helium is inert. As the first stars congealed out of the expanding gas, there were no planets because there was nothing to make them out of. There was no life because there was no carbon and no nitrogen and no oxygen. Our existence on a rocky planet depends on generation after generation of stars, fusing heavy elements in their cores and ejecting them into space to become the raw material for solar systems. The fireworks couldn't start until gravity had used its long reach to gather matter into concentrations dense enough to counter the omnipresent cosmic expanse. This took several 100 million years. But then, the pockets of spherical collapse ignited legions of stars that could slam atomic nuclei together hard enough for them to fuse and populate the periodic table for the first time. Hello, Lynn Jersey. Hi, Ono, it's Anna. How you guys doing? I was meaning to ask you, Ono, is it Anna or Anna or something else? Because I want to get it right. Because I noticed that there's only one N. And I don't want to be butchering it with my American accent. Every carbon atom in our bodies was once in a star in a remote region of space more than 4.5 billion years ago. Some atoms have cycled through multiple generations of stars. Their myriad stories played out over eons until they were co-opted and incorporated into our fleeting human story. We are made of stardust. Understanding the way in which the products of stellar fusion enrich the nebula that form the sun and planets requires finding primordial material in the solar system. The most pristine samples available are certain types of meteorites and comets. There may be as many as 1 trillion comets, and they spend most of their time far from the sun and earth in the deep freeze of space. Material from the outer solar system has been radioactively dated back to 4.567 billion years, which is taken to be the formation epoch. The spherical comet cloud extends to 100,000 Earth-Sun distances, and it's a tenuous relic of the time when the sun switched on for the first time. In the outer part of their orbits, comets are dark and dead, but they become lively and visible when they approach the sun. This diaphanous shroud of frozen worlds holds important clues to our origins. And that's the end of that section. Rhymes with banana. Okay, so Anna. Okay, cool. Thank you. It's so cool to be made of stardust. It is. It just it makes you feel like a part of something big, you know? What kind of planets will evolve around me? I don't know. What kind of planets have evolved around you? Because you were stardust before, you might be stardust after, and like, you know, maybe you were part of a star that exploded, you know, 100 million years ago. That's pretty cool. Mind blown, yeah. Everything is connected. All right. Catching a comet by the tail. To gather stardust, first you have to catch a comet by the tail. That's quite a trick, and the mission designed to capture material from a comet was one of the most ambitious NASA had ever undertaken. The Stardust spacecraft was launched on February 7th, 1999 from Cape Canaveral on a Delta II rocket. It was about the size and weight of a fully laden refrigerator, and it consumed a similar amount of power, 350 watts. Stardust had to survive the rigors of deep space, so it was built around a coffin-sized aluminum frame called a spacecraft bus that provided the basis for a number of interplanetary probes. It was sheathed in a material called Kapton to protect it from micrometeorites. Kapton is the same material as used for the outer layer of spacesuits since the Apollo era. Stardust's destination was an Earth-approaching comet, Wild 2. And I have a figure for you guys, and it's so pretty. There it is. Oh, it's not a figure. I always call it a figure because it used to be like charts and stuff. This is just a cool picture. So this is a artist's rendering, a visualization of the Stardust spacecraft approaching Comet Wild 2. And we're going to learn more about Wild 2 as I read. And you know what? I'm going to leave this up for the next paragraph because it's a pretty picture, so you guys can look at it for longer. Why Wild 2? I've just realized I can make this full screen, can't I? Oh, that's so much better. That's so much better. Okay. Anyway, I'm a streamer. I know what I'm doing. It's fine. Okay. Why Wild 2? The vast majority of comets not only spend more of their time in the very distant solar system, but they never even range within the orbits of the planets. Another set of familiar comets, like Halley's, make periodic passages into the inner solar system and close to the sun, where they grow spectacular tails vaporized from ice mixed in with the rocks. A third and very special class of comets is those that are brand new visitors to the inner solar system. Wild 2 had a fairly uneventful life for 4.5 billion years, until 1974, when it passed within 1 million kilometers of Jupiter, and the gas giant's strong gravity changed its orbit. As a result, its orbital period shrank from 43 years to 6 years, and it began to visit the inner solar system, approaching to the distance of Mars from the Sun. By the time Stardust encountered it, Wild 2 had only made 5 trips around the Sun, so it was almost unaltered from its original composition. Imagine being a naturalist when an exotic and poorly understood animal that normally roams in remote forests is suddenly standing in your backyard where you can study it in detail. By contrast, the more famous Halley's Comet has made more than 100 passes close to the Earth and Sun, so it has been heavily altered by solar radiation. I'm going to switch back to me. Hi. Cat Sleuth, you got a copy of the book and it was autographed by Professor Impey. Oh, that's so cool. I don't even think mine is autographed by Professor Impey, even though I work for him. It is not. That's a shame. I should have had Matthew make Chris autograph these before he sent them over. That's funny. That's awesome, though. Nice. Always fun to add some special autograph books to the collection, you know? All right. After a comet had I'm going to start that over. After a comet has passed close to the sun 1,000 or more times, it has been baked dry and is little more than a stone. Wild 2 contains frozen liquids and gases like water, carbon monoxide, carbon dioxide, ammonia, and methane, called volatiles, in abundance. As it was launched, Stardust didn't have enough energy to reach its target. So the spacecraft was sent back towards Earth for a gravity assist maneuver. As we've seen, a gravity assist is a clever way mission planners steal energy from a more massive object to boost a spacecraft's velocity and overcome the sun's gravity. Typically, the spacecraft comes up on the larger object from behind and gains some momentum as it whips by. Since a planet is so much more massive than a spacecraft, the slight slowing of the planet is undetectable. So nobody in the United States was any the wiser or looked up from their breakfast on the morning of January 15th, 2001, when Stardust flew by Earth and grabbed some of its energy to get out to Wild 2. On the way, it even managed an opportunistic flyby of the small asteroid Anne Frank. Mission controllers tried to sneak up behind Wild 2 to minimize the relative speed of the two objects. Even so, Stardust was moving 13,000 miles per hour, or 5 times the speed of a rifle bullet, as it flew through the glowing coma of the comet. It took 72 close-up photographs. That may not seem like many, but keeping the relatively small comet in the camera field of view during such a fleeting and high-speed encounter was a major feat. The images showed a surface riddled with depressions, with flat bottoms and sheer walls, ranging in size from dozens of meters to several kilometers. The comet itself is irregular in shape and 5 kilometers in diameter. The features are impact craters and gas vents. 10 vents were active when Stardust flew by. The neatest trick Stardust had up its sleeve was gathering material from the comet tail. Ashes to ashes, dust to dust. Behind this somber incantation is astronomical fact. All of the solid objects in the universe were built from microscopic dust particles, stardust. The probe was designed to capture material too small to see in its 8-minute ride through the comet's tail, and then its long ride home. The basic goal was to bring back 2 kinds of material that might speak to our origins. One was comet particles that would pepper the aerogel as it swept through the tail, particles dating back to the birth of the solar system. The other was samples from much rarer impacts due to interstellar dust, particles that might be older than 4.5 billion years, and so would have had to come from previous generations of stars. To do this, it deployed an instrument that looked like an outstretched tennis racket in a cover. Inside the racket was an extraordinary substance called an aerogel. And that's the end of that section. Now we're going to learn about aerogel. Aerogel, to me, I know it's not this, but doesn't it sound like a really stronghold hairspray? Or is it just me? Combination hairspray, hair gel. Aerogel, you know? Aerogel be like, you look like a tennis racket. Like, I could see that next to, like, I don't actually know any brands of hairspray that would be at the store. I haven't bought hairspray since, like, high school. When I had to have my hair really straight because I was in the marching band. I was in color guard and had to spray your hair down like a helmet. All right. I have the mic wire, and I have to decide if I want my arm under it to hold the book or above it. So that's why I just fidget a bunch before I start a section. Okay. Solid smoke. Aerogel was created in 1931 as the result of a bet. Stephen Kistler wagered a colleague that he could replace the liquid inside a jam jar without producing any shrinkage. In other words, he thought he could fill the volume with something that had the same structural properties, but was completely dry. The material that won the bet was 99.8% air and has the lowest density of any known solid. Aerogel is made by extracting the liquid from a gel by supercritical drying. This allows the liquid to be slowly drawn off without the solid matrix. This allows the liquid to be slowly drawn off without the solid matrix. Matrix. I know how to say it. I've watched the movie. without the solid matrix of the gel collapsing under its capillary action, as would occur during evaporation. The first aerogels were made of silica. More recent ingredients include alumina and carbon. If you touch an aerogel, it feels like styrofoam or the green foam that flowers are often pressed into. Pressing on it softly doesn't leave a mark, and pressing on it firmly leaves a slight depression. But pressing down sharply enough will cause a catastrophic breakdown of the dendritic structure, making it shatter like glass. It's light and strong, supporting 4,000 times its own weight. Aerogel is 1,000 times less dense than glass, and the myriad tiny cells of air trapped inside the material make it one of the best insulators known. Engineers at NASA's Jet Propulsion Lab learned how to make extremely pure aerogel, and it was used as an insulator on the Mars Pathfinder mission. Peter Tsu is the wizard at JPL who fabricates aerogels. Because of the importance of his skills, he was named Deputy Principal and Investigator on Stardust. I want to find a picture of this stuff. Marching band represent, yeah. Gotta love marching band. I want to find a picture of aerogel to show you guys, because mostly I want to know what it looks like, because I have no idea what they're talking about. Sorry. It's just wild. I'm going to show you. What the hell? Oh, this is it's like slightly unsettling. In a cool way? So this is apparently aerogel. Look at that. It doesn't look real. That looks fake, doesn't it? It's just very strange. Oh, that's not a good picture. Like what? Oh no, I don't want to save the image. Huh. It looks like the ghost of an object, right? Like it looks like something was there. A diet sugarless Jell-O. Yeah, honestly, it's so weird. Oh, that's so bizarre. That's what ghosts are made of. That's ectoplasm, actually. I'm sorry, NASA. You don't have aerogel. You made ectoplasm. It looks like one of Veritasium's video thumbnails. Yeah, it totally does. I love Veritasium. All right, let's keep learning about this weird stuff. Okay. With Stardust, the challenge was to capture small particles moving at 6 times the speed of a rifle bullet without vaporizing them or altering them chemically. Aerogel is perfect for this job. The rigid foam that's not much denser than air slows the particles down and brings them to a relatively gentle halt, each one leaving a carrot-shaped wake 200 times its size. Imagine firing bullets into a swimming pool filled with Jell-O. Hey, Jell-O. There you go. It is diet sugarless Jell-O. Stardust aerogel was fitted into a module the size and shape of a tennis racket that swung out when the spacecraft approached the comet. One side was turned to face Wild 2, and the other side was turned to face interstellar dust encountered on the journey. Before and after use, the module was stored in its protective sample return capsule. Stardust flew within 150 miles of the comet on January 2nd, 2004, and headed back to Earth with its precious cargo trapped like tiny flies in a silica spider web. On January 15th, 2006, Stardust returned home after 7 years and nearly 3 billion miles of traveling. First, the mission controllers did a short rocket burn to divert the spacecraft from hitting the Earth, leaving it with just 20 kilograms of fuel. Then, they fired 2 cable cutters and 3 retention bolts to release the 46-kilogram return capsule, and watched as springs on the spacecraft pushed the capsule away. The capsule streaked into the pre-dawn California sky at 29,000 miles per hour, faster than any man-made object had ever been returned to Earth. The heat shield and parachutes worked flawlessly, and the capsule landed in the Utah desert at 5:10 a.m. The few people up and outside that morning saw a fireball and heard a sonic boom. Within 2 days, the package containing the aerogel was opened in a cleaned room at the Johnson Space Center in Houston. Stardust was subject to maximum containment restrictions, since it returned material from an extraterrestrial object with the potential to host life. In practice, the risk of infecting the Earth with alien life was low, since any known organism would almost certainly be destroyed by the high-impact speeds in the aerogel. But NASA took no chances. The mission was carried out under a Category 5 planetary protection policy, which is even more stringent than Biosafety Level 4, the protocol used to deal with hemorrhagic fevers like Ebola and Marburg. That means sterilization by heat, chemicals, and radiation before the spacecraft is launched, and a requirement that the return samples are handled in a secure facility and never come into direct contact with humans. Members of the team opened the sample return package in a clean room just down the hall from where hundreds of kilos of moon rocks are kept, brought back by the Apollo astronauts. The room was 100 times cleaner than a hospital operating theater. They were delighted to see the aerogel segments littered with particle tracks, looking like burrows left behind by microscopic creatures. The mission had clearly been a success. That's the end of that section. And they referenced a plate image here. When they reference plate images, if you're following along, you'll probably see it. But when they reference plate images, there's a different section of full color photos in the middle of the book that are a little harder to find. And figure out when they're going to play them. But, oh, okay, I can find that. It's a picture of the aerogel, like, array on Stardust. So let's find it. There it is, yeah. Hey, yeah, there it is. All right. Not the highest quality image, but still the right image. So this is the this is what they call the tennis racket looking thing. This is what it looks like. So all of these, it's an array of these little aerogels. So these are each little box is these little silica. I think they said it was silica for this one. Silica aerogels that would swing out on an arm from the spacecraft, and one side would like hit, quote unquote, the comet tail. It's not a solid object, but it would like take stuff from the comet tail, and then I think the backside was intended to take samples of the just intergalactic medium, so they could compare what was like just in space and what was coming from the comet. So that's pretty cool. It's pretty neat. Here's another picture of it. It's very far away. Not the best image quality. It was early 2000s, but you can see that array as well here. So yeah, cool stuff. All right. Stardust at home. Scientists all along anticipated that tracing our primordial origins with interstellar dust would be like looking for a needle in a haystack or a piece of grit in a gel block. They estimated that while the side of the collector that faced the comet debris might collect 1 million particles, they'd be lucky to gather a few dozen from the side trawling for dust from interstellar space. Such was the case. One side of the aerogel was peppered with trails from comet particles. But interstellar dust was very rare and difficult to spot among all the blemishes and markings that the other side of the aerogel had suffered after 7 years in space. Imagine searching for a few dozen ants nestled deep in the grass of a football field. So the 200 members of the international science team decided to get some help. Stardust at Home, as in like at home, has engaged nearly 30,000 members of the public around the world to search for interstellar dust. The archetypal citizen science project was SETI at Home, where the spare CPU cycles of millions of PCs were harnessed to analyze chunks of radio data in order to search for transmissions from intelligent aliens. SETI at Home had distributed computing as a model, and no thought or intervention was required by people who participated. Stardust at Home is more like Galaxy Zoo, where human eyes and brains are harnessed in pursuit of science goals and participants must undergo training. Citizen science is one of the exciting recent developments in outreach and the democratization of research, where interested members of the public get online training in categorizing and sifting through large amounts of data, and then are able to contribute to the creation of new knowledge. Occasionally, these are very attentive. Sorry, I couldn't read that word for a second. Occasionally, these very attentive amateurs make important discoveries. You did the study at home thing with your PC. That's so cool. That's awesome. Yeah, it sounds like it's almost similar to the way that like Bitcoin is mined or something, where it just like essentially takes your computer and like the computing power that you're not using, they can use, but you know, in a cooler science way than mining Bitcoin, it seems like. Yeah, that's really cool. All right, let's. The raw material for Stardust at Home is a huge number of images made with an optical microscope, which can automatically focus at different depths in the aerogel. A set of 40 images of a small area are taken with the focus ranging from just above the surface to 100 microns into the aerogel. These images are turned into an animated sequence, or movie, so the viewer seems to move through the aerogel. Altogether, 1.6 million movies were needed to cover the 1,000 square meter surface of the collector. This huge number is part of the reason help was needed. Starting in August 2006, Stardust movies were made available to the general public. Each eager participant first had to undergo a short training session and take a test to show that they could indeed recognize particle tracks. Then they were unleashed on the haystack. The signature of a cosmic dust particle is a hollow wake that ends in a tiny particle, often no bigger than a micron in size. And we have a figure of that. Huh. Nope, that's not. There it is. So this is, it's the ejecta in aerogel. So this is what the comet dust impact looks like. And it's wild because it does just look like a landscape shot almost of something blowing up in like the sky. But it's cool. You just run it in the background, especially when you aren't using it, and it just does a thing. That's really cool. Yeah, that, I don't know if SETI at Home is still a thing. I don't believe that this Stardust at Home would still be a thing because it's been a good amount of time and they have they have a finite amount of data, so. But yeah, that looks pretty cool. Okay. A million such particles plowed into the aerogel. Of these, only 10 were large enough to see by eye, 1/10 of a millimeter or larger, and only one was as big as a millimeter across. Computer programs are unable to reliably identify telltale signs of a particle impact, and they can't be trained since such detections haven't yet been made. Additional information has come from the aluminum foil detectors, which were also peppered with dust impacts. Citizen scientists can't get instant gratification from the project. They have to use the virtual microscope program in a web browser and report their results to Stardust at Home headquarters in Berkeley. Each movie is sent to 4 users who each scan it independently. Only if a majority of users claim a particle detection does it go to Stardust science team for confirmation. What do the volunteers get in return for their labors? Mostly online certificates and the knowledge that they're contributing directly to an important science mission. Bruce Hudson from Ontario in Canada did a bit better. He had suffered a stroke and turned to the Stardust mission as a good way to pass the large amount of time he had on his hands. Sorry, there's emergency vehicles going by my house right now. Working up to 15 hours a day for over a year, he not only found the first confirmed interstellar dust particle in the aerogel, he then found a second, named them Orion and Sirius, and he'll be a co-author on the paper that results. Hudson might be amused by the irony that astronomers rarely give names to asteroids or craters less than a kilometer across, yet he put names on objects a billion times smaller. Interstellar dust is distinguished from comet dust by chemical analysis. Particles from deep space are glassy and contain lots of aluminum, along with manganese, nickel, chromium, iron, and gallium. Researchers take particular care not to drop or lose the 7 interstellar particles that citizen scientists have now found. It would cost $300 million to replace them. Yeah, I would hope they don't drop them. Jesus. Gotta be careful. If it seems rather too high-tech and difficult, you can take on the somewhat easier task of gathering comet and asteroid dust in the comfort of your own home. Or at least on your roof. Each year, 10,000 tons of micrometeorites and 100 tons of space dust land on Earth, and a little of that material will also land on the roof of a house. They're not recoverable from the ground because they're too similar to particles in the dirt. The best scenario is a sloping metal, tin, or slate roof with no overhanging trees. Collect the runoff from a day or more and filter it sequentially with a window screen. Sequentially? I guess so. And so filter it sequentially with a window screen and then a finer mesh to remove all leaves, paint flakes, and other artificial materials. The next step involves using a very strong magnet, such as a neodymium, a rare earth magnet, easily obtained by mail order, to gather metallic morsels from the sludge that remains. This will isolate the primary metallic particles, but many terrestrial forms of debris can be magnetic, so the last step involves a handheld magnifier or cheap microscope. With a magnified view, the rounded, melted, and pitted shape of micrometeorites readily distinguishes them from more mundane terrestrial metal particles. Following this method patiently and carefully will net you a number of particles from deep space, without leaving home, and for a much lower price tag than several $100 million. Just imagine the person that drops them. Oh my God, right? That's like, I always, that's the end of that section, by the way, so we're going to pause for a sec. But I always think of, what was that mission called? That poor mission. Genesis. Oh, poor Genesis. I don't know if you guys know of the Genesis mission, but back in, when was it? In the 90s? No, early 2000s. Much more recent. So 2001 to 2004. It was a probe to go hang out by the sun, take in a bunch of solar wind particles, bring it back so they could analyze them, right? So it had these like huge panels, and then it would fold up the panels and bring it home. And it was quite expensive, as it is. I think it was like the first mission to look at these like solar wind particles, because I don't think we had done that before. And they had a little accelerometer that is part of the I guess propulsion method. I don't know. It's part of the thing. And it's supposed to tell the computer in the probe when it gets to terminal velocity, when it was re-entering the Earth, to deploy the parachute and start its like descent maneuvers, right? And they installed it upside down. So it never got to terminal velocity because it got to negative terminal velocity, and then it crashed into the desert. And it was just so sad because like it's another thing where it's like I think they were able to recover like pieces of the plates. Oh, it just looks so sad. Oh, this poor thing. You see it? That was its landing. Oh, poor thing. So I think the data was like stored in here or something. So like they did get some of the pieces. I'm pretty sure. But the problem was they were looking at solar wind particles it's a similar thing with this comet stuff. Like they're super, super small, and like you need to make sure that they're completely like haven't been touched by anything else, because like they could so easily get contaminated by Earth stuff. And like there were definitely holes punctured in, you know, this containment part of this thing, if not everything being shattered. And it was just, you know, and like they've said at NASA, like it wasn't like anyone's, I mean, obviously it was someone's fault, but they're not going to say that like, oh, it was Greg's fault, or anything, because they've said like it's a very easy mistake to make. It's like a piece of metal that's like this big. But damn it, Greg, I know. But I always think about that when it's like they say like don't drop the one of 7 samples that we have of a comet, of comet dust, and it's like, yeah, you gotta be careful. Don't drop the solar wind particles. Whoops. Yeah. Oh, that's funny. Apparently, this mishap is similar to the original event that inspired Edward A. Murphy Jr. to formulate the now famous Murphy's Law. But yeah, so that's your random space tangent of the day, I guess. About Port Genesis. One day, I don't actually know if we've gotten any samples from the solar wind since then. They may have kind of pushed that to the side for a little while. But anyway, let's get back to Stardust. So, Stardust surprises. Stardust had some surprises in store for scientists working on the mission. The first came during the flyby. Team members and comet experts expected Wild 2 to be bland-looking, like a large black potato. Instead, the 72 images sent back to Earth revealed a dramatic scene. Oh, and there's a figure, so I'm going to pull it up and then keep going. Oh, beautiful. Okay. There were kilometer-sized holes bound by the vertical and sometimes overhanging cliffs, spiky pinnacles hundreds of meters high, and numerous jets of gas and dust surging into space. Some of the holes didn't look like the kind of impact crater found on Mercury, the Moon, and every other airless surface exposed to space. The ravines and chasms indicated that the surface is very young and is constantly being created and altered by dynamic processes within the comet. Some of the jets were on the dark side of the comet, proving that they are not generated by the action of the sun. Wild 2 doesn't look like any other comet or asteroid that's been imaged by spacecraft. A related surprise came as the spacecraft flew through debris escaping from the comet. It was expected that the rate of particle hits would increase with time, reach a smooth peak, and then decline as the comet rapidly disappeared in the rearview mirror. Instead, the impact rate surged and fell in bursts, presumably as the spacecraft passed through jets of dust escaping from the surface, and the breakup of cometary clouds as the ice holding them together evaporated. But yeah, so if it wasn't clear, this picture is an artist's concept of the comet Wild 2 as seen by Stardust spacecraft during its close approach. So these jets are released as the comet approaches the sun and starts to lose some of its like gas and dust due to the heat. So yeah, very cool. The most exciting discovery came in 2009 when a team at Goddard Space Flight Center reported the discovery of the amino acid glycine in tiny particles they were analyzing. It's not a total surprise that comets contain molecules like amino acids, but their survival intact in material traveling at thousands of miles per hour was unexpected. An isotopic study of the glycine showed it was not a contaminant from Earth. This discovery shows that at least one of the essential ingredients for life can be delivered by comets. And since most stars are thought to have comet clouds, comets would be an important delivery system for delivering prebiotic molecules to Earth-like planets, so setting the table for life. Another unexpected result was the discovery of iron and copper sulfide minerals in Wild 2 that could only have formed in the presence of water. This means that the comet had spent some of its time at balmy temperatures in the range 50 to 200 degrees Celsius, where water is liquid or steam, so it's not the frozen snowball that everyone expected. Often in science, a simple model or theory formed based on the limited data has to be modified or even discarded when better data are gathered. Nature is messier than our wishful thinking. The Stardust mission has played an important role in retooling the conventional ideas of comet structure and formation mechanisms. It was long thought that short-period comets formed from materials that condensed beyond the orbit of Neptune in the cold Kuiper belt. Long-period comets, by contrast, were presumed to have formed at higher temperatures closer to the Sun, among the giant planets, and then subsequently ejected, primarily by the gravity of Jupiter, to orbits that extend halfway to the nearest star. The discovery of trans-Neptunian objects that feed both the short and the long-period comet population complicates this simple picture. Data from Stardust have complicated it further. Our direct information on comets is still modest. The first probe to reach a comet was launched in 1978 and approached Comet Giacobini-Zinner, providing support for the dirty snowball theory. Comet Halley's first visit to the inner solar system in the age of spacecraft was in 1986 and received visits from an armada of spacecraft. Giotto, Suisui, is that how you say it? Suisei, Sakigake, Sakigake. I hope I'm not just butchering these, but I'm sure I am. Vega 1 and Vega 2. 15 years later, Deep Space One flew by Comet Borrelly. Stardust came next, and in 2005, Deep Impact excavated 10,000 tons of material from Comet Tempel 1 by smashing into it at 23,000 miles per hour. When Stardust returned its payload in 2006, it was the first time we had gathered physical samples from any other place than the Moon. As the only human relic to go on a multi-billion-mile journey and return home, Stardust earned a very auspicious resting place. In 2008, on NASA's 50th anniversary, the sample return capsule went on display in the Smithsonian Museum's Milestones of Flight gallery, alongside iconic artifacts such as the Apollo 11 command module, Charles Lindbergh's Spirit of St. Louis, and the Wright brothers' 1903 flyer. Rethinking comets. The comet cloud defines the outer edge of the solar system, extending 1,000 times further than the planets from the Sun, and a significant fraction of the distance to the nearest stars. It had always been presumed that these small bodies were frozen relics from the formation epoch, essentially unchanged in 4.5 billion years. The expectation was that comets would be made of dust from a previous generation of stars, or pre-solar grains. That's why the mission was named Stardust. Instead, something quite unexpected was found: fire and ice. Comets contain ice that formed in the frigid zone beyond Neptune, but the bulk of a comet's mass is rock, and that rocky material seems to have formed under conditions hot enough to vaporize bricks. The comet particles embedded in Stardust aerogel included two ingredients that are found in meteorites, debris from asteroids that formed between the orbits of Mars and Jupiter. One is chondrules. Yeah, sure, we'll go with that. One is chondrules, rounded droplets of rock formed in many primitive meteorites that melted and quickly cooled as they orbited the sun. The other is a much rarer mineral called a calcium-aluminum inclusion, irregular white particles of very unusual chemical composition that can only form at very high temperature. The Stardust team puzzled over this discovery, but the implication seemed clear. Matter that formed readily in the inner solar system was somehow transported to the edge of the young solar system, where the comets formed. Wild 2 does contain grains of pre-solar stardust material, but they're very rare. Comets are not made of material left over from other stars. They're made mostly from material that formed close to the sun. As such, they provide insights into how planets and moons were built 4.5 billion years ago. Stardust's primary contribution to planetary science is verification of the idea that there was extensive radial mixing of material in the solar nebula, just as the solar system was forming. Also, comets are more physically diverse and variegated than anyone imagined. Each of the comets where we've got up close and personal, Halley, Borrelly, Tempel 1, and Wild 2, have different shapes, surface textures and features, and levels of activity. Comets may be modest in size compared to planets and moons, but their role in planetary systems is anything but modest. They deliver water and organic building blocks to life to terrestrial planets. And as we know from studies of our geological record, when they hit a planet, they can decisively alter the history of ecosystems and even the entire biosphere. It's appropriate that all human cultures have been fascinated by comets and viewed them as harbingers of life and death. To learn more requires an increase in our modest amount of direct information. So it was very exciting when Stardust was given a new lease on life after its sample return. In 2007, NASA approved the new exploration of Tempel 1, NEXT mission, and returned to the site of the Deep Impact mission in 2005. Stardust had conserved just enough hydrazine fuel to make a second journey to a comet, and the goal was to observe the impact made by the earlier spacecraft and see any changes on Tempel 1 caused by its last close approach to the sun. Deep Impact's cameras were blinded by dust released from the impact. In early 2010, a controlled burn ensured Stardust would approach at the optimal speed. The flyby was challenging because the camera had to catch the correct side of the tumbling comet nucleus while coming up on it at 7 miles per second. Appropriately, our first second date with a comet took place on Valentine's Day, 2011. Stardust showed that the 500-foot wide crater created in 2005 was indistinct and had a mound in the center, indicating that much of the ejected material had fallen straight back down in the weak comet gravity. The results indicated that the comet nucleus was fragile and only weakly held together. All good things must come to an end. For Stardust, the end came on March 24th, 2011, when mission controllers deliberately ordered a burn to completion. They told the spacecraft, which was already running on fumes, to fire its main engines until there was no fuel left. NASA used the final burn to refine fuel consumption models for these kinds of engines, ensuring that Stardust gave useful data right up to its last gasp. The next day, project manager Tim Larson put the spacecraft into a state called safe mode, turned off the transmitter, and walked away from the console. Mission accomplished. Hello there, USMC. Welcome to the chat. We're reading about Stardust, the NASA mission to catch a comet tail. I'm going to take a sip of water really quick before we continue. All right. It must be wild to be a project manager on one of these, or like a PI. I think that's primary investigator. Or is it principal investigator? Something investigator. And then just like be working on this for like years and years, and then just it's done. And you're like, oh, what do I do now? You know? All right. Looks like we have a few more sections left and a few more pictures, so let's do it. We are made from stars. In August 1929, The New York Times science section ran an article titled, "The Star Stuff That Is Man." Astronomer Harlow Shapley had been popularizing the point that humans are the mere byproducts of stars. In a radio talk series a few years earlier, produced by the Harvard College Observatory, Shapley pointed out that, quote, "We are made out of the same materials that constitute the stars," end quote. In the Times article, Shapley similarly observed, quote, "We are made of the same stuff as the stars. So when we study astronomy, we are in a way only investigating our remote ancestry and our place in the universe of star stuff. Our very bodies consist of the same chemical elements found in the most distant nebulae," end quote. At the time, some were disconcerted to think that humans might be little more than the product of fission and fusion occurring in stars. Cosmologists have good evidence that all the hydrogen and most of the helium in the universe have existed since close to the time of the Big Bang. Hydrogen, the simplest element, is truly primordial, while most of the helium was formed soon after in a process known as primordial nucleosynthesis, or Big Bang nucleosynthesis. Quote, "The primordial nuclei of the matter constituting the universe were formed in the first 3 minutes," end quote, explains CERN theoretical physicist Luis Alvarez Gaume. Quote, "The cosmic oven produced a number of nuclei, made up of about 75% hydrogen and 24% helium. Small amounts of deuterium, tritium, lithium, and beryllium were also produced, but hardly any of the other atoms that make up our bodies and the matter around us. Carbon, nitrogen, oxygen, silicon, phosphorus, calcium, magnesium, iron, etc. All of these were formed in the cosmic ovens of subsequent generations of stars. As Carl Sagan put it, we are just stardust, remains of dead stars," end quote. The Oxford English Dictionary lists a definition for the term stardust as, quote, "Fine particles supposed to fall upon the Earth from space, cosmic dust," end quote. The OED likewise cites one published commentary from 1879 that claimed, quote, "The very stardust which falls from outer space forms an appreciable part," quote, "of the mud," end quote, "of the mud accumulated on the ocean floor." In fact, the estimate for interplanetary dust particles swept up each year by the surface of the Earth as it turns through space is a substantial 10,000 tons. But that's a tiny fraction of the material added to the seafloor. The most pristine reservoirs of stardust or interplanetary dust are comets. Having formed early in the life of our solar system, approximately 10 million years after the sun's protoplanetary disk stabilized, comets spend most of their time in the cold, extreme outskirts of the solar system. As a result, comet nuclei are largely preserved from heating, melting, and collisions with other planetary bodies. The ice composition and dust grains of comets reveal elements present in the solar system's primordial past. Nuclear fusion reactions in stars create heavier elements by processing or fusing together lighter atomic nuclei. The base of the fusion pyramid is the fusion of hydrogen into helium, which occurs in the Sun and low-mass stars. Stars approximately the mass of our Sun can also synthesize helium, carbon, and oxygen, but thereafter they may never reach a dense enough or hot enough state to fuse yet heavier elements. Massive stars have the ability to fuse their hydrogen to produce helium, carbon, and oxygen, but then progress in successive stages of evolution to neon, magnesium, silicon, sulfur, nickel, and iron. Iron is the most stable element, so typically the fusion chain stops there. Still heavier elements are forged 2 ways: by the slow capture of neutrons in the atmospheres of massive stars, and more rapidly by stellar explosions known as novae and supernovae. Since rarer, larger mass stars are required to generate the heaviest elements, these elements are cosmically scarce compared to the light elements hydrogen and helium. The first generation of stars probably formed approximately 200 to 300 million years after the Big Bang. According to current theoretical ideas, none of those stars still exist, and certainly none have yet been found. They have since exploded in novae, or massive supernovae, collapsed into black holes, or have otherwise expanded their fuel and burned out. The oldest stars currently are generations removed from the first stars that shone in the universe. Astronomers estimate that approximately 25 novae occur each year in an average galaxy generating interstellar dust enriched with heavier materials. From the clouds of gas, dust, carbon to... Sorry, I'm trying to figure out the way to emphasize. From the clouds of gas, dust, carbon, silicon, and metals produced by repeated generations of novae and supernovae, new stars and their attendant planets are born. A nova is a sudden brightening of a star believed to occur when the outer layers of a star are pulled by gravity onto the surface of a companion white dwarf. Pressure due to the mass that accumulates on the white dwarf causes nuclear fusion of hydrogen into helium at its surface, that in turn blows material off the surface of a white dwarf. One type of supernovae is an extreme form of a nova, where mass... Sorry, I got confused by what they meant there. But one type of supernova is an extreme form of a nova, where mass acquired from a young companion star causes a white dwarf to begin carbon fusion and explosively detonate. Another type, a core collapse supernova, occurs when a single massive star exhausts its nuclear fuel and suffers a core collapse followed by explosive detonation. In comparison to a nova, a supernova will produce 1,000,000 times the energy and can for weeks shine as brightly as all the stars of an entire galaxy. In the case of the Milky Way, that's equivalent to about 400 billion suns. A supernova is a prodigious alchemical event. One that detonated in a nearby galaxy in 1987 generated enough stardust to build 200,000 Earths. The Milky Way formed approximately 10 billion years ago, but our sun is only 4.5 billion years old. The sun and its neighboring stars were likely born in a nearby region of dense, coalescing interstellar gas and dust. Isotopic studies of meteorite samples indicate that our sun formed from the detritus of a massive supernova explosion in nearby space roughly 1 million years prior to the formation of the protoplanetary disk that became our solar system. We know this simply by the presence of metals that our sun could not have produced, such as the iron that makes up the Earth's core. Other than hydrogen, which is primordial and dates back to cosmic genesis, almost all the other atoms in the universe have been recycled, silent witnesses to amazing trips through fiery cauldrons and into frigid space, some experiencing multiple adventures. Unfortunately, no atom bears the imprint of its particular passages through the core of a star. Astronomers can only describe their origin statistically. That's the end of that section. Ooh. All right. What's everybody doing today? What's on everyone's I have to stretch. Oh my gosh. What's on everybody's to-do list today? My day's just starting out, so I've got a bunch of stuff to do after this. But I know for some of you guys it's a little later. What are you up to? Let me know. Just stardust in your eyes. By number of atoms, humans and all other living creatures are roughly 63% hydrogen, 26% oxygen, 10% carbon, and 1% nitrogen. Not only the iron in your blood or the calcium in your teeth and bones, but every living organism is made from recycled stardust. John and Mary Gribben emphasize that, quote, the nitrogen in the air you breathe and in your DNA, along with most of the carbon in your body, had a previous existence as part of a planetary nebula and was expelled from one or more red giant stars. End quote. The lead in a pencil, potassium in bananas, zinc and selenium in vitamins were all forged in stars. nickel in coins, oxygen in Earth's atmosphere, mercury in a thermometer, as well as precious metals such as gold and silver, are examples of the heavy elements forged as stars blow off their outer layers and die. Quote, "This is where neon in neon lighting, the sodium in common salts, and the magnesium used appropriately in fireworks comes from. Carbon burning inside stars." And, end quote. And ultraviolet starlight irradiating the envelope of gases surrounding nearby dying stars can produce large volumes of water, essential to the formation of Earth's atmosphere and oceans, and a key marker for life as we know it. The composition of a comet is the frozen record of the chemical environment of our region of the Milky Way as the sun formed, the sum of generation upon generation of star birth and death. When a comet comes near the sun, the energy reanimates chemicals that have been interred from 4.5 billion years. Fittingly, the comet lights to form a feast for our eyes, and a pale echo of the blinding stellar light in which those atoms formed, long before there were eyes to see them. Hello, Sarah. Sarandi? You're French, so your English isn't great, and you don't understand much of what I say, but I look cool. Oh, thank you. Well, we're reading a book called Dreams of Other Worlds. I think it is most of... Again, I don't know if you can understand this, but most of Professor Impey's books are in multiple languages. Let's see. Yeah, if any of you guys actually... are here. No, I don't want the translation of the words. I want the translation of the book. I'm not sure. But a lot of Professor Impey's books are temporarily out of stock on Amazon. Only one left in stock. You guys all just been buying this book? Some of his are in different languages. I know we have some in other languages. I just don't know where to find them. Besides the shelf at our office. But thank you for hanging out, Sarandi. I hope I'm saying your name right. Sarandi? Thank you so much. All right. Let's keep on going. Comet impacts as vectors for life. Robert Burnham points out that it was not until the space age that astronomers realized just how pervasive cometary and asteroid impacts are throughout the solar system. Beyond the moon's cratered and craggy surface, NASA's planetary science missions have charted numerous bodies in our star system riddled with impact craters. Those missions reveal, explains Burnham, quote, that by an overwhelming margin, the most common feature in the solar system is the impact crater. Entire planets, moons, and asteroids turned out to be covered with them, at all scales ranging from global to microscopic. Craters or their traces can be found on every solid surface, from Mercury to Pluto, and surely beyond. End quote. It's likely the object that devastated the Siberian taiga near the stony Tunguska River at approximately 7:15 a.m. on June 30th, 1908, was a meteorite. However, the unknown projectile was not made of iron like the meteorite that excavated Meteor Crater in Arizona approximately 50,000 years ago. It is estimated the impactor exploded above the ground with the force of 1,000 atomic bombs, more than adequate to destroy a modern city. The explosion reportedly flattened 830 square miles of forest, leveling 30 million trees, and was heard 500 miles away. Multiple remarks of witness accounts of this event included Multiple remarkable witness accounts of this event included a man 40 miles from the impact site who reported being knocked off his feet by a searing blast wave. Atmospheric pressure waves registered on barographs after racing around the world at hundreds of miles per hour. The explosion apparently caused a local geomagnetic storm that lasted for days. People in London wondered about the strange, glowing atmospheric effects and pink-fringed clouds appearing in evening skies. One British meteor specialist published his observations in Nature in 1908, saying that the night sky over Bristol, England, was so bright few stars could have been seen. In July 1994, comet Shoemaker-Levy 9 broke in the... I just said that weird. Sorry. Comet Shoemaker-Levy 9 broke into fragments that I feel bad. So Randy said that they don't understand much of what I'm saying. It might just be because I keep stumbling over my words. I'm not making it easy for the native English speakers either. All right. In July 1994, comet Shoemaker-Levy 9 broke into fragments that subsequently slammed into Jupiter with an estimated explosive force of 600 times humanity's entire nuclear arsenal, and spewed plumes of material thousands of miles above Jupiter's clouds. Millions globally, including astronomers, world leaders and politicians, and a fascinated public, found themselves captivated by television news reports and images streaming from JPL's designated website. That single comet impact raised global awareness of the very real danger such events pose for Earth's populations. The comet began to impact Jupiter on July 16th. Within 3 days, the U.S. House Committee on Science and Technology voted to establish a NASA program to track comets and asteroids that could threaten the Earth. As co-discoverer of the comet, David Levy recalls, quote, "This vote reflected the nation's fascination and its growing awareness that such a trail of destruction could have been headed at Earth. The initiative was designed to protect future generations of people." End quote. Should the threat of a comet or an asteroid impact be successfully deflected, Levy contends the global attention focused on comet Shoemaker-Levy will have an effect, quote, "rescued our planet." I do look pretty cool, like well-assembled modern-age stardust. Hell yeah. Put that on a shirt. Well-assembled modern-age stardust. That honestly, I might put that on a shirt. That's very good. I like that a lot. Should we make stickers? This is a random thing. Should we make Teach Astronomy stickers? We used to have Active Galactic stickers. I used to have one on something here. I don't think I have one now. But people want stickers. Or like cool, I don't know. I don't know if you guys have heard of Redbubble. It's a website where you can like make designs and then they'll essentially print the stuff if people want to buy it on certain things. We need merch. Teach Astronomy sticker on your laptop or on your coffee cup. Hell yeah. So maybe I'll mock up some designs. That could be fun. Put the design on some of that stuff and see if it's something people want. Yeah, I'll think about that. We do need merch. I want a sweatshirt. That says Teach Astronomy. That would be cool. All right. Though the devastation of comet impacts is obvious, these primordial snowballs may very likely be the reason for life on Earth. Given their ubiquity, it's believed that cometary impacts are a common vector by which life may have emerged on Earth. As noted previously, researchers working with the Stardust data reported finding the amino acid glycine in Comet Wild 2 samples. Amino acids are comprised of what is commonly referred to as CHON, C-H-O-N, or carbon, hydrogen, oxygen, and nitrogen atoms, and the molecules that CHON, along with phosphorus and sulfur, can combine to make are all chemical ingredients of DNA. Comet and meteorite impacts on Earth could have dispersed such organics or even synthesized them. Oh, and I just realized I think I forgot to show you guys a picture. And that's not cool because we like pictures here. So this is from before, and it says, "Comets are carriers of both life and death. This artist's impression shows a large comet impact on the early Earth. Cometary material includes water that led to the Earth's oceans and some basic building blocks of life, like amino acids, but occasionally impacts by comets have caused devastation and destruction over the Earth's history, including several mass extinctions in the past 500 million years. So, this is just an artist rendering, but maybe that's what it looked like. I would love to not see that in real life, though, I'd have to say. Would love to keep that as an artist rendering. Okay, let's keep going. Science writer Connie Barlow claims, quote, "Our ancestors include ancient stars. Stars are part of our genealogy," end quote. She means that if we want to discover our origins, we can't simply peer into a microscope at possible progenitor organisms. Instead, we need to look to the stars, where heavy elements necessary for life, like carbon, are forged. But we also can attribute our genetic makeup to comets and asteroids that may have deposited on Earth the chemistry for life. All known organisms are the products of their DNA, and some components of DNA have been detected in meteorites. In 2011, NASA scientists reported finding in meteorites, quote, adenine and guanine, two of the 4 so-called nucleobases that, along with cytosine and thymine, form the rungs of DNA's ladder-like structure, end quote. DNA is the coded information in our cells that determines biologically who and what we are. Quote, "At the center of the ladder-like DNA molecule lie ring-like structures called nucleobases. It's these tiny rings that scientists at NASA and the Carnegie Institution for Science in Washington found in 11 of 12 meteorites they scrutinized," end quote. Meteorites, if not jettisoned from a neighboring planet, are remnant chunks of rocky debris left over from the sun's formation. Given that such meteorites deliver organic molecules to Earth, molecules from our star's earliest days are inevitably in our DNA. I'm stumbling over words now because now I'm thinking of merch designs while I read. I'm gonna be honest with you guys. I'm like, wow, now I want, like, I could have a little hoodie and, like, I could embroider a little because I embroider in my spare time. I do a lot of things. I could say Teach Astronomy, but then, like, on the back it has the, like, TA logo with, like, the star thing that I do, like, you can see it on the sides here, the stars or something, and it's just like, oh, it'd be so good. And now I'm distracted, but I need to finish reading this. So I'm gonna focus now, and I'm gonna hold that creative energy for later. All right, where was I? We will start after the quote. I think that's a little bit farther back, but that's okay. Meteorites, if not jettisoned from a neighboring planet, are remnant chunks of rocky debris left over from the sun's formation. Given that such meteorites deliver organic molecules to Earth, molecules from our star's earliest days are inevitably in our DNA. Scientists reported in the journal Nature having found fossils of multicellular life dating back 2.1 billion years, roughly 1.5 billion years prior to the Cambrian explosion. These fossils and black shales in West Africa rewrite the history of when multicellular organisms first emerged. Microbial life on Earth predates even this. Biologists, astronomers, and astrobiologists, now faced with recalibrating the timescales on which life began on Earth, are reworking our appreciation for comets and their critical role in dispersing stardust through the solar system. Stardust's mission to capture the interplanetary dust grains that pervade our star system is an attempt to understand not only how our sun originated and evolved, but also the characteristics of the early solar system that led to the origin of life. What we learned from the Stardust mission is that comets and asteroids harbor the building blocks of life. 20 different amino acids, occurring naturally in a wide number of arrangements, produce the proteins that create all living organisms on Earth. John and Mary Gribben report, quote, "Formic acid, the stuff that some ants squirt out as a defensive weapon, and the stinging ingredient in stinging needles, and methanamine and methanamine are two of the polyatomic organic molecules that have been identified in dense interstellar clouds. Together, they combine to form an amino acid, glycine. End quote. As James Lovelock, originator of Gaia theory, has observed, quote, "It seems almost as if our galaxy were a giant warehouse containing the spare parts needed for life." End quote. Perhaps the universe is built for life. The Gribbon suggests that the chemistry for life is endemic to the entire universe. They assert that, quote, "One of the most profound discoveries made by science in the 20th century is that the universe comprises the raw materials for life, and that these raw materials are the inevitable product of the processes of star birth and star death." End quote. Though the normal matter that makes up stars, planets, and stellar dust clouds constitutes only a small fraction of the total matter in the universe, most of which is dark and still mysterious, the stuff of stars nevertheless provides all the components necessary for life. Quote, "The raw material from which the first living molecules were assembled on Earth was brought down to the surface of the Earth in tiny grains of interplanetary material, preserved in the frozen hearts of comets." End quote, writes Gribbon and Gribbon, who eloquently observe, quote, "Those grains themselves literally, not metaphorically, formed from material ejected by stars. The manna from heaven that carried the precursors of life down to the surface of the earth, was literally, not metaphorically, stardust. And so are we." End quote. That we are made of stardust is not to be disparaged. It's likely that life has emerged on planets orbiting other stars in galaxies far, far away. If so, it's certain that the blood in their veins and the calcium in their bones, should they have them, were forged in the fires of their suns. That's the end of that section. And it looks like we have just about a page and a half or so left. So we will finish this one up and do a regular little wrap up. Before we go, though, since we mentioned it, what kind of stuff? It looks like CJ SideQuest and Lynn Jersey both said we need merch. Suggested the Teach Astronomy sticker on a laptop. That would be cool. Is there any other stuff that you guys would want? Any specific designs? Because, if I have some free time this week, I do some digital art stuff. That's how I made our lovely little emotes. Well, okay, that's a lie. I made one of the lovely little emotes. I made this one. The little heart. But these were just wonderful pictures that we happen to have that I made very small. But t-shirts. Catsley said t-shirts. That's a good idea. That would be cute. Let me know what you guys would be interested in. Just throw it in the chat while I finish this section. It could be like actual items or like specific design stuff for quotes or things like that. If you have any ideas. If not, that's okay too. All right. A world by any other name. Comets and asteroids provide evidence of the formation epoch of our solar system. They represent the pristine stardust of which we are made. They're implicated in life and death in the evolution of life on Earth. But they're minor bodies of the solar system. The 3 targets of stardust study are a motley, misshapen collection. There's 55, 35, and Frank, 3 miles across and shaped like a right-angled prism. There's Wild 2, similar in size, with a pitted and coruscated surface. And there's 9P/Temple, slightly larger and shaped like a potato. Are they big enough to be called worlds? Are they substantial enough to have a place in our dreams? Yes, absolutely. They may be too small to hold an atmosphere, but comets and asteroids have unique shapes and topographies that imbue them with personality. Our technology is good enough to throw a gravity lasso around a space rock that ventures near us and steer it into Earth orbit. Comets contain water ice and organic material needed to sustain life, and the hydrogen and oxygen in the water are all that's needed to make rocket fuel. A comet retained in high Earth orbit would be a perfect jumping-off point for manned exploration of the outer solar system and beyond. Asteroids also contain valuable metals and minerals. According to one estimate, the mineral wealth in the asteroid belt amounts to $100 billion for every person on Earth. Wild 2 probably contains around $20 trillion worth of precious and industrial metals, and over $100 billion worth of platinum alone. In fact, the precious metals we do have were gifts from comets in the early days of the solar system. Metals present when the Earth formed settled directly to the core, while the planet was molten. Those we can reach in the crust were dusted onto the planet by later waves of comets. Space mining aside, a small, barren rock might not be worth calling your own. In 1967, the 1967 United States Outer Space Treaty prohibits any state owning or controlling the moon, an asteroid, or a comet. But the treaty has a loophole, since it doesn't specifically exclude the ownership rights of an individual. A small world might seem limiting, but think of the pleasure in owning a world the size of a small town, and surveying the domain like a colossus. The gravity of Wild 2 is so weak you would literally be as light as a feather. A small push and you could escape your world and sail into deep space. And think of the glittering minerals, a hoard magnificent enough to power all the dreams ever dreamed. And that's the end of that chapter. That was nice. I liked that. That was fun. I love that Professor Impey and Holly Henry say that, like, you know, a small world might seem limiting. To own a small world. I currently don't even own my 1-bedroom apartment. That's more limiting, Chris. That was a cool chapter. Very poetic. Yes. Hi, Bill Nash. Did you just get here again? We just finished. I feel bad. I feel like you've gotten here at the very end every session, these last couple. Charlie said, let's take a rocket ship to space theme something. That'd be cool. You're always late. I'm sorry. Turn on your notifications. Although I know that sometimes Twitch notifications don't work. So, I also understand. But yeah, I think that's pretty much it. So next time, you're trying to establish a trend. In the case of your own funeral, you want to be late to that too. I love it. I love it. Hopefully that's a long way off, but, you know, start early. Or I guess start late. Because you're always late. Anyway. So next week we are going to be reading about Soho, which I actually don't know about. I don't think. What is Soho? Hold on. We're gonna find out what Soho is. I'm sure it's like means something, and we have WeHo here. Soho, I guess, is probably South Hollywood, but not to NASA, because there are more important things. The Solar and Heliospheric Observatory is a spacecraft built by a European industrial consortium. And there's more details and stuff. It has discovered over 4,000 comets. Oh, that sounds fun. It began normal operations in May of 1996. That's only a few months before I was born. That's crazy. Vicky, let's see if we can let's take a rocket ship to space on the next Voyager record. Hell yeah. When's Voyager 3 coming out? We got to make sure that we get to contribute to this this next record. I don't know if we actually told you guys this, but Active Galactic is on Perseverance, I think. The Perseverance disc that has like a bunch of names. I don't remember how many names, like 3 million names or something like that. We submitted Active Galactic as one of the names. So we are on there. Not as Teach Astronomy as our other name, but it's pretty cool. But yeah, I think that's pretty much it for today. So thank you guys all for hanging out, for chatting, for learning about Stardust and comets with me. That was really fun. I didn't know literally anything about the Stardust mission until today, so it was really fun to read about it and learn with you guys. And also now you have started me thinking about doing merch designs. So I don't know the logistics behind that. I've only ever done one merch thing, and it was for my podcast. Hey, you should go listen to Cryptid Cape. If you like listening to my voice, voice the main character on Cryptid Cape, you should go check it out. But a 70s rock album cover theme for the merch. Oh, that would be so cool. Wait, I love that. Like a the way that NASA does their like vintage kind of poster. I guess they're not. Are they vintage? Yeah, vintage travel poster. NASA vintage travel poster thing. That style would be really cool. Yeah, so I'm gonna start thinking about that. Might take a while. I don't know. Again, merch logistics and things. But if people seem interested, then we'll see what we can do. And as far as the rest of the schedule this week, on Wednesday we have our astronomy. I think it's gonna be actually having another person this time, because I know we promised you guys a guest last week, but then it turned out that it was midterm week and all of our fellow students were very busy. So we had to skip that, but I think we'll be able to have a guest on this week, and she'll be able to come on and talk about her research at the University of Arizona and some of the cool stuff that she does. Michael will talk some more about his research. It'll be a whole good time. That's on Wednesday, and then on Friday we have I just totally forgot what I was saying. On Friday we have the amateur astronomy with Matthew, and I believe last week we had a little bit of a confusion because I totally forgot that, time zone change happened, and like got confused in my head because they don't change times, we change times, the whole thing. And I believe it's still scheduled as 11 on, no, it was scheduled as 10, and then we accidentally did it at 11. So I think we will, I'm going to talk to Matthew about that today, and we're going to figure out a time, either 10 or 11, maybe 9. I don't know. We'll figure it out, and it will be on the schedule by the end of today. So that will be all sorted. But yeah. Oh, you're 5 episodes in on the podcast. Oh, thank you so much. Oh, Ox Bowman, you were multitasking, so no comments. No worries. Thanks for listening. I hope you enjoyed. Yeah, definitely these reading days are good too. I mean, not for me. I cannot multitask while I do this, but it's nice to like have something on in the background when you're doing stuff like this. So I totally get it. But thank you so much, Oh No, It's Anna, for listening to the podcast. And Lynn Jersey as well, although I knew that you listened to already. And I think that's pretty much it. So a quick reminder to anyone who found us today, if you would give us a follow, that would be great. It helps out the channel a lot, and make sure that you won't miss anything when we go live in the future. Also, we are Twitch affiliates, so you can subscribe if you want to. It would be super cool. And I think that's pretty much it. So yeah. Oh, and if you are a subscriber and you're on the Discord, I've been meaning to say this like at the end of every stream, but if you're a subscriber and you're on the Discord, but you're not part of the subscriber specific like chat or channel thing, just message me and let me know, because sometimes I try to add you guys, but if your names aren't the same on Discord as they are here, I can't find you. But I can fix that for you if you want me to. So yeah, I think that's about it. But thank you all for hanging out, and I hope you guys have a great rest of your day. And I'll see you on Wednesday.